All right, we're going to conclude our trigonometric function unit with some applications here. And applications, just a really funny way of saying word problems. Trigonometric functions have lots of real life situations. They're used for a lot of different modeling situations with recurring behavior, repeated cycles, that sort of thing. And often you're going to be asked to create graphs to model the situation and then to do some kind of interpretation. As with most word problems that you've seen throughout your mathematical career, there's no one set algorithm to solving the problem. You really just want to see if you can create a visual model. So sometimes that's a diagram that you would use to help you solve. Sometimes you need to be creating an equation to help you solve. But at the end of the day, that's not the point of the question. The point of the question is actually you doing the interpretation bit. So that's what we're going to do here today. I've picked 3 examples of questions that are very common for trigonometric function applications. One is a tide question, one is a pendulum question, and another one is sort of a riding the bike, like a circular kind of question. All of these are periodic behavior. And I'm just going to sort of talk through how I would solve them. Perhaps you would have a different strategy as you are established as mathematicians at this point. But maybe you can sort of see the process that I'm going through and some of the thoughts that I'm having. All right, let's start with our first example here. During high tide, the water depth in a harbor is 22 meters, and during low tide, 6 hours later, it is 10 meters. Draw a graph to represent the water height for a 24-hour period starting at high tide. Find the equation to represent the function, and then what is the height of the water at these different time periods? Okay, so we're going to start with the graph here. We're going to pick a scale that is relevant to the question. It didn't say how, well, it says we need to draw a graph for a 24-hour period. That's as far as we need to go. So our x-axis is going to go from 0 up to 24. So let's start by filling that in. It looks like I can just go up by 1s. And on my thicker black lines here, I'm going to go up by 4s. And now the question is, in terms of height, how are we going to set our y-axis? We know during high tide, the water height is 22 meters. That's as high as it's ever going to go. The lowest is going to be 10 meters during low tide. So the highest up my x-axis, or my y-axis, I should say, that I need to go is 22. It looks to me like I can go up by 2s. And that'll be a successful scale. Awesome. From here, so we picked a scale. Now we're going to plot some key points based on information that's in the question. Okay. So we know that, and let's do this in blue because it's blue water. We know that it starts at 22 meters. It's starting at high tide. And then at 6 hours later, we have low tide. So at 6 hours, we're down to 10. The way the tides work is they come in and out and in and out. So the tide went out there. 6 hours later, it's going to come back in all the way up to high tide. And then we'll go back down for another 6 hours at 18. And then 24 back up here. Okay, so I could give this a sketch to show our periodic function to the best of my abilities. Oop. So it's going to look something like that. Okay, we've plotted our key points. We've connected with a smooth curve. Question number 2 says, find the equation to represent the function. Okay, we're going to do that just like we did in our previous lesson in 3.4, because now we have a graph. So now we can actually figure out all of the key pieces of information just based on this. Let's start with our max and min. We know this from the question. The max is 22, the min is 10. I can use this to find my midline. Halfway between 22 and 10. I take the average. 22 plus 10 is 32, divided by 2 is 16. So my midline, and you could sort of see that on the graph anyways, my midline is 16, and that is my K value, right? That's my vertical shift. I can find my amplitude now. My amplitude, recall, is the distance up from the midline to the max or down to the min. I'm just going to go max minus midline is 6. My amplitude is 6. If you got that straight from the graph, no problem. There is no horizontal shift here. D. And I apologize, I wrote K instead of H. H is our midline. There's no horizontal shift. This is a cosine function. I can see that right there. And my cosine function is starting on the y-axis. There is no horizontal shift. But there is a change in period. It's obviously not 2 pi. We need to figure out what the K value is going to be. I can see my function starts at 0 and it completes 1 cycle after 12 hours. So my period is 12, and I use this to find my K value. 12 is 2 pi over K. Let's do this over here. K will be equal to 2 pi over 12, and we can just simplify that to be pi over 6. So my K value is pi over 6. And we can write our final equation. Six cos of pi over 6x, all plus 16. Amazing. All from that graph. Then the last part is we actually need to do the interpretation. So the question, yes, it asked us to draw a graph, and yes, it asked us to find the equation, but now we need to find the height of the water after 9 hours, or sorry, after 3 hours, after 9 hours, and after 20 hours. All of these moments are imprecise on the graph. This is something I drew by hand. At the 3-hour mark, it looks like, you know, I'm crossing the midline there. I don't know if that's true or not. At 9 hours, we're up here, we're around 18, and at 20, we're pretty low. We're at like 12 and a half. But that's just estimating using the graph. What we should actually be doing is we should actually be substituting these numbers into our equation and then solving. So that's what we're going to do. Our first one was at 3 hours. Our second one was 9 hours. And then the last one was 20. Cool. Let's go ahead and solve. F of 3, so we have 3 and a 6 here that we can substitute, or we can simplify. Cosine of pi by 2. Cosine of pi by 2 simplifies to negative 0.5. Times 6 will be negative 3. And negative 3 plus 16 is 13. So At 3 hours, the tide is 13 meters high. We can repeat that. 4 at 9 meters. Simplify. The 9 and the 6 simplify. I divide both of them by 3, and I have 3 pi over 2. Cosine of 3 pi by 2 is also negative a half. 6 times negative a half is negative 3, plus 16 is 13. So at 9 again, it is 13 meters high. And then last but not least, we had to figure out how high our function was, or how high our graph was. I should say how high the tide was at 20 meters. So I'm going to simplify. I can divide both by 2 to have 10 pi by 3. And that's actually a third. Six times a third is 2, and so I get 18 meters high. Okay, so these are the actual interpretation questions that I was asked to do. And because this is a word problem, we're going to conclude using a therefore statement. Therefore, at 3 hours and at 9 hours, the tide is 13 meters high. At 20 hours, the tide is 18 meters high. And we can always go back to our graph and just sort of double check that that makes sense. At 3 and at 9, we said it was 13. All right, 3's here. All right, that's not that far off. I must have drawn the graph a little bit high. Here's about 13. That's not that bad. 9 would be the same. So again, I was just drawing my graph a little bit higher than I needed to. So I could correct that if I wanted. At 20, it said that it was supposed to be at 18 meters high. And so obviously something has happened with the math here. So we're going to go back and double check to make sure that I've done the math correctly. Let's go back here. Found the problem. I had typed it into my calculator wrong. I'm not sure what I typed in, but 10 pi over 3 is not a third. It is in fact negative a half. Just like all of these. So the answer, once again, is going to be 13. So I can change my sentence here. At all of them, at 3, 9, and 20, the tide is 13 meters high. Yay. Okay, let's do another example here. This is our pendulum example. A pendulum swings back and forth in the same place at a constant speed. So if you don't know what a pendulum is, think those really old clocks that had the thing dangling from the clock and it swung side to side. That's a pendulum. So it's swinging back and forth at a constant speed. The displacement from its resting position is described by this function. d of t is equal to 6 sine pi over 3t, where d is the displacement in centimeters and t is the time in seconds. Draw a graph for the function starting at t equals 0 for 2 cycles. Okay, so we have a couple of things that we need to figure out here. We need to figure out what labels to put on our axes first. That's going to be the big one, okay? We know we have a sine function as well, so we're going to be starting at 0. Starting at y is equal to 0. So let's figure this out here. We know our period is equal to 2 pi divided by k. And I have been given a k value here of pi over 3, so I'm going to substitute that in. And if you're uncomfortable doing this sort of like division where you've got a number divided by a fraction, you can always do this. I can do 2 pi divided by pi over 3, and that allows you to use that keep change flip that you might be more comfortable with. Now we can see here that my pi's are going to cancel out, and I'm going to be left with 6. So my period here is 6, and the value or the unit of measurement is seconds because we're talking about time. So I know that it takes 6 seconds for me to complete 1 full cycle, and I've been asked to sketch 2 full cycles. No problem. Now we know what label to put on our x-axis. It looks to me here like we've got lots of space, so I can count up by ones once again. This will be 4, 8, 12, 16, 18. Actually, we can even go slower than that. We can go up by halves. There we go. Yeah, lots of time because one period is only 6 seconds. Okay, in terms of our amplitude here, we can see that the amplitude of our function is 6. We can also see that there is no vertical shift. So I wrote a 0 instead of a 6. When there's no vertical shift, that means that our midline is on the x-axis. Usually, sine functions go up by 1 to their max and then down by 1 to their min. Here, we're going to be able to figure out our new max and min using our amplitude. Our amplitude is now going to be, we know that our max will be 6 up, and our min will be 6 down. So that's as high that we need to go on our graph here, so I can use that information to inform my scale. And it looks like I can just count up by ones. Awesome. Okay. We need to draw a function of the graph, draw a graph of the function starting at t equals 0 for 2 cycles. Sine functions, we know, start at the midline, go up to the max, and then down to the min. And so that's exactly what I'm going to do. I'm going to start at my midline. My max is, I should say 1 cycle takes 6 seconds. So I'm going to put my end there. Then I'm going to draw my halfway point, which would be at 3, and is also on the midline if I'm thinking about how to sketch sine functions. Then I go halfway between my start and my halfway. That's 1.5. And at that point in time, I go up to my max. So 1.5, I go up to 6. And then halfway between 3 and 6 is 4.5. And at that point, I need to go down to my min. Perfect. That's just 1 cycle, though. I need to draw a second cycle. So I'm going to do that all again, just starting at 6. So if I start at 6, I end at 12. And then halfway between 6 and 12 is 9. Halfway between 6 and 9 is 7.5, and there I go up to my max. Halfway between 9 and 12 is 10.5. That sounds right, 10.5. And I'm going to go down to my min there. Yeah, it looks about right. I've got my key points on my graph now, so I'm going to go ahead and sketch and do my best to keep it looking like a sinusoidal function. all right, not bad. Not bad. So we've got our function sketched here, and that is literally all the question was asking us to do. We didn't need to do any kind of interpretation questions here, so we're done with this one. And last but not least, let's do a third example here where we are riding a bike. This is a cyclical motion, which is super common in solving trigonometric functions. Okay, when you ride a bike, the height of your foot above the road is a circular function of the time you have been pedaling. If you think about it, you're sitting on a bike. Your pedal goes around and round and round in circles. An equation to model this height is h of t equals 20 minus 15 cos 2 pi of t. Where h is the height in centimeters, highlight that, that's useful. Sure, height in centimeters, and t is time in seconds. First, we're being asked to graph this equation for 2 cycles. I do not have some graph paper. Okay, we're going to have to add it, no problem. This function is written in a way that may make sense for the scenario, but we're going to rearrange it so that it makes more sense based on what we are used to. I'm just going to rewrite it down here. Where I'm going to have my vertical shift at the end. There we go. That's better. Okay, so we need to graph the equation for 2 cycles. I'm going to cheat here and I'm going to make my background graph paper. I can't. That's okay. Let's grab a ruler and draw some scales. Well, let's be smart about it. Let's figure this out first. Let's figure out our period. Let's start with the period. Period is 2 pi over k. Our k value is 2 pi. So our period is just 1. That is a very fast moving pedal. We need to sketch it for 2 cycles, and so I know my x-axis is only going to go up to 2. That's it. In terms of the midline, my midline is located at y is equal to 20. That's midway through my function. And I can figure out my max and my min by starting at the midline and adding my amplitude. My amplitude here is negative 15. So to figure out my max is going to be 20 plus negative 15. My min is going to be 20 minus negative 15, which will leave me at 5 and at 35. So the max and the min terminology here is actually going to switch because we have a negative leading coefficient. So I'm just going to erase that. It's no big deal. This is going to be our min, and this is going to be our max. And again, that's happening because we have a negative leading coefficient. You start at the min first. Our cosine function is going to look like this, like an n, where you start at the min and then you go up to the max. Min first. Okay, so the y-axis that I need to draw, we already said for x has to go up to 2. The y-axis needs to go all the way up to 35, so no big. I'm going to sketch that here real quick. My function never drops below the y-axis, so I only really need quadrant 1. And let's be precise about this. This is 1, 2, 3, 1 over 2, oh, whatever, let's just write a half. 1.5, 2.5. Okay, now all the way up to 35. 35. I can do that just. So we'll go 5, 10, 15, 20, 25, 30, and 35. Okay, this one's going to be a little bit rougher because I don't actually have a grid that I'm working with, but that's okay. We are truly just trying to draw a sketch. Okay, I'm going to start with my midline as a guiding line here at y is equal to 20. Perfect. We already said this is a negative cosine function, so I'm going to be starting at my min. My min here is 5. We have no horizontal shift, so I'm going to be starting at 5 on the y-axis. I'm going to go up to my max. Or sorry, I could also say I'm going to end at 5 at 1. After 1 second. At half a second, halfway, I need to be going up to my max, which is 35. So it's going to be all the way up here. And then halfway between the two, I'm going to be landing on my midline. Hopefully that's about right. Repeat that for the second cycle. So I start at 1 and 2, go up to my max halfway, and then draw my midline points halfway between those guys. All right, and let's do our best to draw. This is going to be very tall, very narrow. Okay, we've done our best. Once again, it does not look like a zigzag. We have made every effort to include some smoothness. Even look at the bottom here. Look at that nice swoop, because we know that if we continued, it would hop right back up. So I'm not drawing a straight line. I'm drawing a beautiful little swoop there. So nice. Okay, we've drawn our graph. Check. How far above the ground is your foot at t is equal to 0? At t is equal to 0, that's my starting point, and I'm starting at 5. I don't actually need to plug that into my equation here. I am 5 centimeters above the ground. Awesome. What is the radius of the pedal arm? Okay. I hope you can see that if we had, and I'm just literally going to draw a pedal on here. We'll make it brown. My pedal starts at the bottom of my bike. And it goes all the way up to the top and then all the way back down. That's like doing a full circle on my tire. Or on my gear thing, whatever. Right? It goes all the way to the top and then it goes all the way back down. The height difference here between 5 and 35 is the diameter of my circle. You can sort of think that those are like the pedals, and this is like the little bit in the middle holding it all together, and they're spinning back and forth. So my diameter is between 35 and 5, which is 30. I have 30 centimeters of diameter. I'm asked for the radius. The radius is going to be half of that, which is going to be 15 centimeters. And an easy way to find that is our amplitude. If you're ever asked to find the radius of the circle, you just look at the amplitude. It's nice and easy. It's the distance from the middle all the way to the top. That's the radius. Okay, check. How far above the ground is the center of the circle the pedals make when they go around? The center of the circle the pedals make, that's right here. We've already drawn that dot, and that is 20 centimeters above the ground. That's our midline. You could think that might be like a point of rotation or something along those lines. That's what you might call it. Okay, we've done it here. So to recap, Create a graph if it's asking you to create a graph. Even create a graph if it's not, because it's easy to interpret stuff from a graph, and it's easy to check your answer like I did in question 1, where we had done the math wrong. I had done the math wrong, and I could see very quickly on my graph that I had done something wrong. You want to be using those graphing strategies that we've reviewed throughout the unit in order to create accurate graphs. And then you can either use the graph or you can use the equation to answer the question that you have depending on the scenario. In our third example here, I could just look at the math that I had already done. I could look at my graph, I could look at my equation in order to answer. As we saw with the first question, we actually needed to substitute in the values into the equation in order to get a precise answer. So that might be the other thing that you need to do. Okay? And that's it. This is all you need to know for applications of trigonometric functions.